Hello all, welcome to AK App Projects. This is AK. From today onwards, I'm gonna start a new series that is Verilog HDL, Verilog Hardware Description Language. This is actually for the PC students who are eagerly want to join in the field of VLSI. The Verilog Hardware Description language is used for the design and verification engineer in VLSI. So there is no proper content in the YouTube. So I decided to start this Verilog HDL along with my membership the aptitude series because I am from the EC background. I know Verilog HDL very well. So I will try to convey the most important and information of the Verilog HDL and will cover each and every topic of the Verilog in detail. So this is the first part video of the Verilog HDL. I hope you guys make it successful. The first part video is introduction to Verilog. Okay, yeah. In this, we are going to discuss about seven topics. Like what is Verilog, what was used before Verilog, why is the Verilog is better. Then it's their languages. How is Verilog used for Verilog code example? How is Verilog different from software languages like C? What may replace Verilog in the future? Okay, yeah. Let's continue to the video. What is Verilog? Our first topics. What is Verilog? Verilog is basically a hardware description language. Verilog is basically a hardware description language. What is meant by hardware description language? Hardware description language means nothing but the uh, it is used to describe the hardware. What is meant by hardware? See, the hardware means the uh, it is in the form of like a full adder, half adder will be there, right? So for you guys, there is full adder, half adder, and all this uh, multiplexer. This type of circuits will be there, right? So we will write the code for those circuits. It means we will write the functionality of those circuits. For that, we use this language, Verilog, which is a hardware description language. So, Verilog hardware description language is used to describe digital systems and circuits in the form of code. Okay. I hope you understand. I'm gonna get make you ready for the hardware, this backlog hardware description language. The first 2 to 3 videos will be pretty bore. From later on, you will feel very interesting. Okay, so I'm making you to enter in the world of digital system design. Okay, yeah, it was developed by the Gateway Design Automation. Gateway Design Automation is like a company which was developed the Verilog in the year mids of 1980s. Okay, later acquired by the Cadence Design System. Design System is a tool company which we are going to practice this Verilog and we are going to design this Verilog uh, designs digital systems using Verilog in the Cadence design system. Cadence has so many Cadium tools like Xalium for simulation, GNS for synthesis, and so many other tools will be there in the Cadence. So this is a later the Cadence acquired the Verilog. Okay, yeah. Next. Verilog is widely used for design and verification. Design and verification means of digital and mixed signal systems. So, what is the meaning of this line? So, design and verification means nothing but the we are going to use this Verilog language for the design purpose and also for the um, testing purpose, testing in the sense verification purpose. Design, what is meant by design? So I already previously told, right, full header, half header. For to describe this functionality of the full header, half header, we will write a code. That code will be called as design code. Whereas we have to verify, right, whether the code is being correct or not by applying some test cases, which are test cases are nothing but input values, different types of inputs. Okay, different combinations of inputs, test vectors. We will call it as test vectors or scenarios or test cases. So for that we have to write another code to apply the those values. We have to write another code. So that will be called as test bench. Okay, to test the design or to verify the design, we have to write another type of code which will be called as TB. Okay, for the functionality of the design, we should write the design code, which is design code. Okay, yeah. Next, this will be Verilog language is used to describe digital and mixed signal systems. Digital in the sense ones and zeros. Okay, digital in the sense the ones and zeros, right? So whereas mixed signal means it may be analog, mix combination of both digital and analog signals. Okay, yeah. Uh, in, including ASIC. ASIC means application specific integrated chips, which means we are going to design ASIC chips. ASIC chips are nothing but their functionality will be fixed. It means if you are going to design a full adder chip, then it always uh, the chip always does the function of the full adder itself. So it is application specific, which means a particular application will be done. That's it. We can't program that chip. Okay. So using Verilog, we will design those also. Next, and field programmable grade arrays, which means field programmable gate arrays, which means we can reprogram those codes. For suppose we have on FPGA, FPGA chip, FPGA chip, FPGA chip. So it means we can dump our required code into it and test. So again we erase that code and code, dump another code into the FPGA and test it again. So it acts like if you have an idea of Arduino, which is a microcontroller, like in Arduino we dump the code of required application and we reset it and we dump another code, right? So similarly FPGA works like that only. So but it is very high profile high applications we use this FPGA. It one chip will be cost around one basic chip, medium chip will be cost around 14,000. That basis 3 FPGA, there are so many FPGAs. Okay, yeah. Whereas ASIC is nothing but a IC which is uh, restricted towards only one application. It means it is application oriented. It is application oriented. Okay, yeah. Next, it supports a range of levels of abstraction. Range of levels of abstraction. Let me erase this. Supports a range of levels of abstraction from structural to behavioral. Is used for both simulation based designs and synthesis based design. So I have already told that what is in the simulation based design means. So I have told that we will write two different types of codes, which is design code and TB, right, which is test bench. Uh, while we are going to write both, right, for a design. For example, if we have taken half adder, we will write both TB and design. So the design code includes the functionality of the half adder, whereas the TB includes the different types of combinations of inputs that are going to drive this design, whether this design is correct or not. Okay, we will verify that using truth table, and also we will verify using the waveforms like this 0 1 1 0 like this. Okay, so that is called as simulation based design. After, if everything is okay fine, if everything is okay fine, we are getting output waveforms as correct, and also we are getting the functionality of the particular design. For example, half adder, if it is right, the design code is right, then we have to convert this design code into the schematic for that purpose we will use the synthesis based design, that is the conversion of design into gate level netlist. Gate level that synthesis output schematic will be called as gate level netlist. So we will use this Verilog as in both the cases. So this is the thing. Next, the language is used to describe digital circuits, as I previously told, hierarchically starting from the most basic elements such as logic gates and flip-flops and building up to more complex functional block systems and subsystems. This is nothing but we will, for example, if you are going to take half adder, we are going to divide this half adder into subsystems. It means half adder requires one AND gate, right? Uh, for the carry purpose, we read with one AND gate. So, and for the sum purpose, we will require XOR gate, right? So, we are going to divide again these gates into its subsystems. It means smallest unit, so smallest module. So, AND gate again can be divided into some of the transistors, right? So CMOS transistors, right? So we are going to divide it into smallest particles. But okay, again extra code we are going to divide it into small particles, tiny particles. Now we are going to write code for this firstly code for this level, and if we everything fine here, we are moved to the up hierarchy. So we will write code for XOR using these modules. So after if XOR and AND gate also functionality is also okay. After writing design and TB, if the functionalities of AND gate and XOR gate are also okay, we will write the code for the half adder using these tested and XOR gates. Okay, so that the point given here. Next, yeah, it's widely supported in the range of modeling techniques include gate level. Gate level in the sense there are some primitives, predefined things like AND gate. There will be some gates, AND gate, OR gate, XOR gate like this. There are already predefined keywords. Okay, RTL level means it's nothing but the using the equation in the sense logic. For AND gate we represent AB, right? A and B, right? A and B, right? So using this, we will code in the RTL level, behavioral level. Behavioral is similar to like the C language. We don't need any lower details of the design. Simply, we will write the functionality. It means if if both the inputs equal to one, if A equal to one, we will like write like this. If A equal to one and logical operator and b equal to 1, then output should be 1, right, for AND gate. So we don't require any lower details, lower level of details, how many transistors we are going to use, like that information we don't need in behavioral model. So we write like this. Okay, next, when compared to so let me erase this. So wait a second. Yeah. So the next point is, the next is what was used before Verilog. What was used before Verilog? So we use VHDL, which is a precedence language of the Verilog, which is high, very high speed integrated circuit hardware description language. This is also for the digital circuit design and verification of purpose only. Okay, before the development of Verilog, we use it, the primary hardware description language. Okay, yeah, VHDL is developed in the 1980s by the US Department of Defense as part of very high-speed integrated chips program to test, design and test high-speed digital circuits. Okay, yeah. What was used before Verilog? Yeah, VHDL is a complex language. See, complex language that enables designers to describe digital systems using a range of abstraction levels. Here also we have some of the abstraction levels from the low level transistor to gate level up to complex hierarchy systems. From the low level to transistor describing to the gate level up to complex hierarchy systems. Okay. Yeah, it was designed to be more descriptive. It means we have to code more. We have to provide more information about the design and it's flexible than earlier HDLs. Before VHDL also we have some hardware description language such as advanced Boolean expression language. Okay, compared to advanced Boolean expression language, the Verilog is more descriptive and flexible than this. Okay, than able. Okay, yes, despite the development of Verilog and its increased popularity since in the year 1980s, VHDL remains a widely used HDL. At the time of Verilog development only, VHDL remains widely used. It means most of the companies used VHDL at the time of development of Verilog, particularly in Europe. Europe country, we are going to use the VHDL mostly in the time of we, 1980s in the military and the aerospace industries. Europe, military and aerospace industries. Okay. Today, both Verilog and VHDL are widely used in digital circuits design and verification. Both VHDL and Verilog are used for the design and verification purpose, with many companies and organizations using combination of the two languages. Some of the companies also use the combination of these both languages. Uh, okay, yeah. Here is an example for indicate described using the VHDL. Okay, see, this is the code for the indicate in VHDL. Here the colored words are the keywords. Okay, so this is the comment. This is we are going to use the library IEEE. This is the IEEE library name. This is a comment entity declaration defines the inputs and the output. We are going to use the keyword entity. The gate name, this is the name of the circuit and gate. Is a keyword. Port is the used to declare the input and output ports. Okay, we have to use the parentheses. These are the input A, B, and output Y. Okay, yeah, and we are going to use the and the module which is this entity which we have declared right and get we are going to end it and architecture describes the behavior or structure behavior of an indicate. This is also a comment and we are going to use begin and end. Begin and are similar to the uh, curly braces in C. Okay, remember this point. Okay, this is the non-blocking assignment. I will discuss it. And is a keyword to perform the AND operation between A and B. We are going to end it, right? We are going to end the behavioral section. Why Verilog is better than its preceding language? Verilog introduced several important improvements over its preceding language, which helped make it more popular and effective HDL for digital circuit design and verification. There are few reasons why Verilog is considered better than preceding languages. Okay, let us see why it is more better. Okay, simple syntax compared to VHDL, Verilog has simpler syntax compared to VHDL. Okay, which allows designers to write code more quickly with fewer errors. So VHDL is more descriptive and effective, right? Effective in the sense more descriptive. We have to describe more things about our design. But in Verilog, we shouldn't describe more details. We can write also using simple syntax and few lines of code. So this makes Verilog better than VHDL. Okay, better support for behavioral modeling. So I have discussed, right. So it means Verilog provides better support for describing the behavior and functionality of the digital design. So we shouldn't need any low level details of the design. So if you know the functionality of the design, we can code it using the behavioral modeling. Okay, so it supports the range of modeling techniques from gate level. Gate level I already discussed, right? We have some predefined keywords like primitives, which are called as primitives. Uh, those are AND gate and or like this. To behavioral level modeling, which makes it easier to describe the behavior of complex digital circuits. Okay. Yeah. Why Verilog is better than its precedent language? The higher level of abstraction. Verilog provides higher level of abstraction than its sister language. It enables designers to describe digital circuits using concepts such as modules and ports. So in VHDL we use the entity, right? So in Verilog we are going to use module and ports. Okay, remember this point. I'm gonna make you ready to this series so that first 2 to 3 videos will be more descriptive. Okay, we should be patient. Okay, which makes the design process more efficient. Okay, yeah. Better tool support. Due to its increasing popularity, Verilog has better tool support than its precision language. Verilog has a range of integrated development environment tools, IDEs. IDEs in the sense, Verilog has so many companies are using the Verilog tools, and so many companies are uh, making the Verilog tools. Okay, simulation mostly compared to HDL, there are Verilog tools are more in the market. So this also makes the Verilogs to stand out better than VHDL. Okay, Verilog creates a level of abstraction that helps hide away the details of its implementation and technology. We shouldn't mention which technology we are going to use and the details of the implementation. So we should describe just the functionality, then the design will be automatically generated. Okay. For example, the design of flip will require the knowledge of how transistors need to be arranged to be achieve a postage ticket flip. What is the rise, fall, clock Q times required to latch the value onto a flop, among many other technology-oriented details. Power dissipation timing, the ability to drive nets and other flops would also require more through understanding of the physical characteristic of a transistor. So we don't need all this, okay? We just simply need when clock is high, when D is equal to 1, the output will be 1. If we know this, we can able to code. Okay, we don't need any transistor level details and all this stuff in Verilog. Okay, yeah. Verilog helps us to focus on the behavior. So I have told, right. So we just need the information, like for in the case of DC clock, when the clock is high, that is passage. Okay, when the D is also uh, high, the output will be 1. When D is low, when the clock is high, then output will be 0. Okay, so this information is needed, which is much enough. We don't require any details of the transistors. Okay, yeah. Let us see an example for the Verilog. The Verilog code describes the behavior of a counter. See, this is the counter in which we will write the code into the module and module. Between and module and end module, we discuss our code. The CTR is a module name. We have to give some module name. This in this inside the parenthesis, we have to list the port list. Port list is nothing but what are the inputs, what are the outputs. Okay, so this is the vector representation of the output. This is range. We have two types of data types, which are wire and range. The default value of input and output will be wire, so that we haven't mentioned wire here before the up and down and clock and reset. Whereas we are going to use the range because we are going to use this. This is a behavioral model. In behavioral model, we have to use output as range. Okay, this is always which is in behavioral model. It is a block which executes infinite times. Okay, at the rate is a used to declare the events. Whenever the passage of the clock is there, then it should check the reset bar. If reset bar is equal to 1, if reset bar is equal to 1, we have to declare like this, or else if we leave like this means also it will work. Okay, equal to 1, then at at the point of time of passage. Okay, so output will be 0. Else if up down is equal to 1, then it should be incremented by up 1. It should be acts as the up counter. Else output should be down counter. Okay, we have to end it because we have to use the begin and end. Previously I told, right? Begin and end are flower used as a flower packets in Verilog. So in the if statement we haven't used any begin and end because we have only one statement. When there is a else statement, else block, we have so many statements, right? We have another if blo- if and else block, right? So we have to use the begin and end. Again, inside the if and else, we have only single statements in both the if and else blocks, right? So I haven't used any begin and end. So there is no required you are using the begin and end when there is only one statement. Okay. Yeah. The next thing is the counter counts up to the if the up down signal is 1, down if its value is 0. Okay, it resets the counter if the signal reset and becomes 0, making it an active low reset. Okay, because the reset is as reset bar is equal to 1, then output will be become 0, right? So we have to say that it has active low reset. Okay, so simple example shown above illustrates how all the physical implementation details, interconnection of underlying logic gates like NAND and NOR have been hidden while still providing clear idea of how the counter functions. So this is the point I'm discussing so many times, right? So we don't need how the NAND and NOR gates internally are connected. We just those are hidden, right? Those are hidden. We are just providing the how the counter is functioning. Okay, so we are just giving the details how the counter is just functioning. We don't care about how the uh, NAND gate and NOR gates, which type of gates are used internally. We don't care about it. Okay, whether we are getting the functionality that is required by us or not, we will see that only. Okay, yeah. CTR is a model that represents up-down counter. So I have discussed it, right. It is possible to choose the actual physical implementation of the design from a wide variety of different cells optimized for area, power, and performances. So after this, we will convert the design into the synthesis, right? Synthesis, and we convert the design into gate level netlist. Gate level netlist, right? So when we convert this design into gate level netlist, we have to do some optimizations. Optimizations in the sense we have to reduce area of the generated gate level netlist power of the design which we have generated from the design code, and by doing this all this we will get a better performance. Okay, all we are going to do is to reduce the uh, power power and the delay. Okay, so our target is to reduce the area, power, and delay, and to make the chip in the very compact size. So uh, the main aim of VLSI designer is to make the chip in a compact way by reducing the area, power, and delay. Okay, our main focus is on these three things: area, power, and delay. Okay, they are usually compiled into libraries and will be available for us select within the EDA tools at a later stage in the design process. So there are so many libraries like 2 nanometer technology, 3 nanometer technology, 45 nanometer technology, 90 nanometer technology, 180 nanometer technology, GPDK files will be there. So in those files, we will already have the predefined shapes and symbols of the design, uh, and how what is the size of the our uh, uh, NMOS, PMOS in 180 nanometer technology. Those are predefined. Okay, so we will use those, and we will design a circuit, and we will test it. Okay, after completion of our design code, if the design code is correct, it will be taken place in the backend. Okay, how is Verilog different from the software languages like C and Java? Verilog is a hardware description language used to describe digital circuit systems, while C and Java are software programming languages used to write code that runs on general purpose computers. We write C, where using C and Java, we write code for the applications, whereas using Verilog, we write code for the digital circuit systems. Okay, so here is the main differences between Verilog and programming languages like C and Java. So, purpose. Verilog is used to describe digital circuits and systems, while C and Java are used to write software programs that run on computers. Okay, syntax. Verilog has different syntax. Okay, than C and Java. Even though it is somehow similar to the C, but there will be some changes in the syntax, right? As it is designed to describe the behavior of digital circuits rather than execution of software instructions. For example, Verilog describes the properties of wire, edges, logic gates, while C and Java defines the variables, functions, and control loops. Okay, so Verilog has timing delays, whereas in C and Java we don't have any timing delay, right? We don't specify any timing delays, and if in Verilog the timing is most important, most important. While in C and Java we don't that much of importance. There is no that much of importance for the timing. Okay. Execution. Parallel is used to describe how digital circuits should be behave. Yeah, this is the thing I have discussed, right? But it doesn't directly execute code. We are not executing the code. We are just applying the test cases whether the design is correct or not. We will check it and we'll get some waveforms. Okay. Instead, the Verilog code is employed into a hardware configuration that can be implemented in a physical circuit or FPGA. So I previously told, right, FPGA is like Arduino, which is can be reprogrammable. So we will dump, sometimes we will dump code into the FPGA after we get the uh, simulation results. That is, if we get the waveform in a correct way and we get the correct output by after we applying the TV in a sense, I already told, right? We specify some test cases or scenarios or inputs, different combinations of inputs for the design code that we have designed. If everything is fine, the simulation waveforms and the uh, TV test cases are passed, then we will dump the code into the FPGA and we will test it in a FPGA, and we will either manufacture that code into the that code design code into the ASIC chip, or just leave it. Okay. C and Java code, on the other hand, is compliant to machine code that can be executed directly by the computer processor. Testing and verification. We're is easy to simulate in the sense we will get waveforms. We are going to use TB and design code for the simulation behavior of digital systems before they are physically implemented, while C and Java programs are usually tested and verified through software-based simulations or code reviews. Okay, we are going to use some other tools which are different for both the C and Java, and also Verilog. Verilog is completely different. We will get some waveforms. But in C and Java, we don't get any waveforms. We get just console output. Even in Verilog, we will get the console output that is nothing but the test cases that we described in the TV. So whether the it will get what is the test case that we are applied, and what is the output corresponding to the test case. We will get like that in console output. While in waveform we will get signals. Uh, for example, this is the signal of A, this is the signal of B, some like this. So the output corresponding to this will be this like this. Some signal, some sort of signals. Okay, so I'm gonna make you prepare for this weight series. So the first three videos will be boring, even for me to make it's boring. But I'm making you to ready. Okay, nesting of design. In Verilog, the design can be created as modules. So module is the smallest unit in the Verilog. Can be reused. We can reuse it so many modules. Okay, which is not in the case of programming languages like C and Java, where the code is written for a specific purpose. In C and language, we will write code for a specific purpose, wherein Verilog, we will write code for a design, right? So if we are going to write half-headed design, so we can use that half-headed design and make the full header, right? So we will know that full header using half-header, right? Full header using half-header also we have, right? We can, if we are going to write after a design and tested using the TB, now you can instantiation will be there. We can instantiate this half header and make the full header. So it means we are going to reuse this code, right? So this is the point that is given here. Overall, Verilog is specialized language design specially for digital circuits design, using used for general purpose languages like C and Java. Okay. Well, there is some similarities in syntax and programming concepts between these languages. So we use if else, switch case, for loop, while loop, all those things in Verilog. Uh, s- Verilog is quite similar to the C. It means in Verilog, behavioral modeling is quite similar to the C. The only difference is instead of uh, these flower braces in the blog for blog all these blogs we use begin and end, or two things will be there, begin and end will be there, so we use the okay, and also some changes will be there, that is we use some timing delays. We will specify those using hash 10 like this. We use some timing delays, but in C we don't use any timing delays, right? So I will discuss all those things again. Okay. What may replace Verilog in the future? It is difficult to predict exactly what may replace Verilog in the future. Yeah, why? Because uh, it's a designing of an hardware with optimization. Without, if there is no optimization, then we can replace. But there is optimization. There should be optimization, right? So we can't able say that like may be replaced by the AI in the future. Okay, language that may have effect on the future of digital system and design and verification. Okay, yeah. One technology that may affect in the future digital system design senses, which is technique for automatically generating hardware designs from the high level descriptions like C, C++, System C. Okay, we can able to generate the designs circuit from the description. Okay, but we can't able to optimize this. Optimization should be done by the man itself. System also can be done, but it will take a long time. Okay? HLS allows designers to express their design intents and functionality at a higher level of abstractions rather than specifying the details of logic gates and registers, transfers in Verilog or VHDL. Yeah, this is the point. Is HLS means high level senses designers to express their designs, intents, and functionality at a higher level of abstraction. Higher level of rather than specifying the details of logic gates. It means I told right. We will describe only high level details. No. not consider on the low level details like logic gates, registers, and uh, transfers. Okay, register transfers. This could enable more efficient and rapid design of digital system design and allow designers to explore more design space in a shorter period of time. Because of this, describing the behavior of the design, the designers can explore more designs, right? If we the designers are uh, uh, going to specify the low level details, then it takes so long time to make a design. If the designers are using high level uh, behavioral description, so it is very easy to designers to design more number of circuits, right? More numbers of circuit because we are going to describe only functionality of the design, right? Yeah, but only using the functionality of the design, we don't know how the internal circuit will be. So it will be affecting the while optimizing, it will be we will get some uh, issues. So what the designers do is first they usually check the functionality in the high level. Later they convert this high level code into the low level, and they will get a circuit of their design, right? So then they optimize that circuit. Okay. Yes. What very yes. Another technology that may affect in the future of digital system is machine learning. Okay. And artificial intelligence. AI can replace which can have significantly streamline the design verification of process of digital systems. Okay. For example, machine learning algorithms can be used to automatically optimize and generate hardware designs. So it can be happen, but it will require lot of time because the mission should be very it should be like Rajnikant's robo, right? It should be like that. The mission it should be that much power should be there, but nowadays those mission didn't have that much power to optimize. They can generate the hardware description and hardware design, but the mission can't able to generate the optimization. Okay, it can't able to do the optimization. They can't. A mission can't because it optimization should is not a small thing. It's very big thing because to sustain in VLSI design or VLSI industry, the optimization is most required thing. Okay, so optimization, if you know how to optimize your design, then you definitely succeed in VLSI. Definitely. So it's the main thing in VLSI, not the coding, not the syntax and all. So it is all about the optimization. Okay. So replacing these missions using the machine learning and AI, it will take a lot of time. I and also even though if it take a lot of time and even the AI is used to optimize our designs, it can't able to give as the human giving right that much effective it can't able to give like a human. Okay. That thing I can able to say you. There are also emerging HLs that are trying to address some of the limitations of the Verilog and VHDL. There are also research is being going on to the next hardware description language level, such as Chisla and MyHDL are the current going research to the drawbacks of Verilog and VHDL, which are based on more modern programming concepts and provide higher levels of abstraction. So I told right, uh, it will become like a programming language. Simply we have to describe the functionality of the design and the higher level details, not to go into the lower level details like gates and transistors and all. Okay, so I think that's it. Thank you guys. Like, share, and subscribe to AK. For the next video, stay tuned. Uh, Comment me. This was the first video, right? So after 2 to 3 videos, you will be felt very bored. I also felt very bored to discuss these topics, but I'm making you guys to get ready into the digital world. For that, these videos are very very essential because uh, if you're being patient, after 3 to 4 videos, it was only 4 videos. After 4 videos, you will get to know that you're learning, you will automatically be adapted the thing to learn the digital system design. So I'm making these videos. Okay, for first 4 videos will be introduction only. Okay, there is some basic design flow and all. Afterwards, we are going to start with comments and other data types, operators, all these things. Stuff. There is stuff in the in front. Okay, stay tuned to this channel. So if you don't believe me, after I uploaded uh, nearly 10 videos, you watch the video from the comments topic. Okay, then you feel very um so nice. You will feel like so good. Now this it's all the three. Uh, Sorry, let me read the topic, right? So we can't able to say like that. Okay, thank you guys. Let me close this.